Okay, so in this video we're going to be talking about the other two types of wave behaviors. In the last video we talked about reflection and refraction. In this one we're going to be talking about diffraction and then superposition and interference, which go together. And so this wave behavior that we're going to talk about first is called diffraction, not to be confused with refraction. So remember, refraction happens when a wave tries to go from one medium into another medium and it hits a boundary and it bends due to a change in the wave speed. Diffraction does not involve a wave trying to go from one medium to another medium. It happens when a wave hits a wave traveling through just one medium hits like an opening or a barrier or something like that, and then it spreads out past the opening. And so if you look at this picture, this is a picture of diffraction. We can see coming in from the left and going towards the right, this wave is traveling and it hits this opening, this slit, and then after it goes through the opening, it kind of spreads out past the opening. And I can show you a simulation. It's best if you go to YouTube and just look up examples of diffraction. It's very easy to find, but I can show you the simulation. This is with light. We can see there's a light source on the left side. I can change the color if I want to, and I can adjust these slits, the thickness of the slits. We can see the wave is coming and moving from left to right, and when it hits this opening, you can see it kind of spreads out in this circular pattern. Now, what that means is if you imagine taking like a light and shining it at a really thin little hole, that means that if there's like a laser pointer over here, like let's say in the middle, and I'm standing over here, I can see the light even though I'm not directly behind the hole, because the wave spreads out when it goes past an opening, and so that is called diffraction. And you can see this with water waves, you can see this with sound waves, although that's maybe a little bit harder to see. And so that's what diffraction is. Again, this is not the same as refraction, which is what you get when a wave travels from one medium into another medium. Notice, by the way, that the amount of diffraction I get kind of depends on the size of the slit. Okay, so the bigger the slit is, you can see, the less diffraction I get. This is with a water wave. Okay, so imagine like a faucet like dripping in a sink and creating a water wave, and then that wave going and passing through this opening. You can see the wave spreads out past the opening. So again, if you just like go to YouTube and you look up diffraction, you can see lots of great examples. Here are some applications of diffraction. If you've ever heard sound around a corner, that is an example of diffraction. Okay, so here's a boy standing on the left side of the corner, and there's a radio, and there's not a direct line of sight between the boy and the radio because there's a wall there. Okay, but what can happen is the radio can emit a sound wave, and the sound wave can spread out, and when it hits this corner, when it hits this opening, it spreads out past the corner there. And so the boy, even though he cannot see the radio, he can hear the sound can go around the corner because it spreads out past the corner. And so that is an example of diffraction. If you've ever seen an example of like this picture on the right where the door is open just a crack, but you can see the light spreading out as it goes past the opening in the door, that's an example of diffraction. Okay, so there's lots of examples of diffraction. Again, don't confuse this with refraction. That's something completely different. And again, this is a type of wave behavior that applies to any type of wave, whether it's water wave, sound wave, light wave, anything like that. Okay, and so we're just going to do a few quick examples, and then we're going to move on to superposition and interference. Okay, so this example says, in the picture below, which wave behavior is shown? Okay, the hint here is we have a wave going from one medium into a new medium. Okay, so see if you can figure out what type of wave behavior is shown based off of what we talked about in the last two videos. Okay, so this is going to be B. This is refraction. We have not talked about interference yet. We will momentarily. Diffraction we talked about before. Diffraction and reflection don't require going from one medium into another medium. Now they can both happen at a boundary between two media, but refraction is the only one involving a wave traveling from one medium into another medium, and then you can see bending. Okay, so that is B, refraction. And just to do one more example, which of the following wave behaviors is responsible for being able to hear your friend talking to you from around a corner? Okay, so we just talked about that a second ago. See if you can answer that. Okay, so the answer here is C, diffraction. And again, we just talked about that a few slides ago. Okay, so the last type of wave we're going to talk about involves something called superposition and interference. And so the idea behind superposition has to do with what happens when two waves meet each other. Okay, so imagine we have two waves in space, and let's say they're going towards each other. So this is one wave pulse on the left, and this is one wave pulse on the right. And as they approach each other, I want you to pay attention to what happens. Okay, as they pass through the same space, okay, you go from having two separate wave pulses to some kind of combination of the two wave pulses. And then afterwards, they just kind of pass through each other. So if you think of two cars, if two cars go towards each other and they collide, they crash and there's destruction and all that stuff. When two waves pass through each other, they kind of occupy the same space and you get something called superposition. And superposition happens when two or more waves occupy the same space. And then what happens is you basically add the two waves together. Okay, now the trick to doing superposition with waves is understanding that this wave pulse on the left, because it's going up, has a positive value. And this wave pulse on the right, because it's going down, has a negative value. And so that means when they overlap, you get superposition. They're kind of canceling each other out because you have a positive and a negative wave. Okay, now it doesn't have to be that way. I can make them both have a positive value like this. And then what happens is as they go towards each other, remember, you only get superposition when they occupy the same space. The two waves kind of form up and they combine, and then afterwards they keep on passing through each other. Okay, and so superposition is the principle whereby when waves occupy the same space, you basically just add the displacements of the waves together. Okay, and you can either get a bigger wave or a smaller wave, depending on whether you're adding two positive waves, two negative waves, or one positive and one negative. If you have a positive and negative displacement added together from superposition, there's going to be some type of cancellation. Okay, but the principle that waves can add together like that, that's called superposition. Okay, the name superposition comes from the idea that waves superimpose or kind of like overlap with each other. So in the notes, that's what it says right here. It says the principle of superposition is sometimes stated as follows. When two waves interfere, the resulting displacement of the medium at any location is the algebraic sum of the displacements of the individual waves at that same location. Now that's a very complicated way of saying basically a sum is when you add things. Displacement is just how far is away from the rest position. This is basically just saying when two waves occupy the same space, you add them together. Okay, that's basically what superposition is. Now, because of superposition, because any type of wave has superposition, you get something called interference. Okay, now interference, it says in the notes right here, interference is the phenomena when which occurs when two or more waves meet while traveling along the same medium. Okay, and there's two types of interference you need to know about. Okay, so here's how this works. If you have two waves, okay, let's say two wave pulses, while they are overlapping, there's going to be superposition. Now, if you're adding, let's say, a positive wave pulse to another positive wave pulse or negative to negative, you're going to get a bigger value than either of the two individual wave pulses alone. In other words, if you were to measure the height of these two wave pulses while they're overlapping, you get an overall bigger wave. This has a name. Okay, this is called constructive interference. Okay, so the two waves are interfering with each other, and it's constructive because they're basically forming a larger wave. They are constructing a larger wave. Okay, and so basically the way you would find the size of that wave is you would just add these two displacements together, and we'll do an example of that in just a second. Okay, now it doesn't have to be two positives. If I flip these two waves and I add them together, we can also get constructive interference. Okay, and the characteristic, so here is the constructive interference that we get. The key characteristic of constructive interference is if the wave that forms from superposition is bigger than either of the two waves by themselves. In other words, if they have the same sign, if they're both positive or if they're both negative, it's constructive interference. Okay, now there's another type of interference that's called destructive interference. And basically the way destructive interference works is if you have one positive wave pulse and one negative wave pulse. Okay, so here is an example of destructive interference. Okay, I've got a positive wave pulse over here, a negative wave pulse over here, and as they occupy the same space, they're superposition. While they're superposition, you're basically adding two waves together, right? Because that's how superposition works. Okay, but if you're adding a positive to a negative, then basically there's going to be cancellation because they have opposite signs. So here, one wave pulse has a height of positive 3. The other has a height of negative 1.5. So while they occupy the same space, they basically add together and form a new wave of height 1.5. Okay, where did I get 1.5? Because 3 plus negative 1.5 equals positive 1.5. So I'm just adding the size of the two waves together. But because one is positive and one is negative, there's cancellation. Now, it's also possible when you have destructive interference to get completely destructive interference. If they're both the same size, but one is positive and one is negative, when they combine, they completely cancel out. Okay, and that's kind of what you can see right here. This is completely destructive interference. Okay, so this would be destructive. A lot of people, I don't know why, but a lot of people like to say deconstructive. I guess they think like the opposite of constructive. Deconstructive interference is not a thing. You should never ever use the term deconstructive interference. That's not a thing. You have constructive and you have destructive. Okay, if they're the same sign, if they're both positive or both negative, it's constructive interference. If one is positive and one is negative, it's always destructive. Not deconstructive, that's not a thing. Destructive, as in like destroy. As in the two waves, because one is positive and one is negative, they're like destroying each other. Okay, that's how you remember the difference between them. Okay, so just to show you how this works, like if you're doing calculations, remember the way that superposition works is while the two waves occupy the same location, you're basically adding the two displacements together, keeping account of the sign. So here, for example, we have a wave where this blue one has a size of, let's see, 1, 2, 3, 4, positive 4, because it goes up 4, and this one is 1, 2, 3, 4. Actually, I'm going to make it negative 3, and I'm going to make it just like a rectangle to make this easy. And so while these two waves are separated, they're just two separate wave pulses. When they overlap in their superposition, I'm basically going to add the two together. And so if you have a positive 4 plus a negative 3, basic math, positive 4 plus negative 3, superposition says that you just add those two together, you get 1. And so that means while these two wave pulses are completely overlapped, I should get a wave that has a size of 1. Okay, and down here you can see I get in the black, I have a wave of size 1. So this is an example of destructive interference. Remember, deconstructive is not a thing. Destructive interference, because one wave is positive and one is negative. And so calculations with superposition are very, very easy because all you're doing is you're basically adding numbers together, keeping account of the signs. Okay, so here we have 4 plus negative 3. Let's say I want to make my second wave positive 2. Okay, and the only problems you're going to see are going to be like these rectangles that are very easy to add. So this is going to be constructive interference when these two overlap because they're both positive. They're both the same sign. And so when they overlap, I'm going to have 4 plus 2, which means that my new wave, while they're superimposing, while there's superposition going on, and they occupy the same space, should have a size of 6, okay, which is bigger than the two waves by themselves. And so let's see if I get that. Okay, here is when they completely overlap, and we see I get a new wave size 6. Notice, by the way, when they're not completely overlapping, I get like a weird shape. Even though that looks really weird, this is what you would actually see. Okay, this is the superposition of these two waves. Okay, as they pass through each other, you can see on the bottom down here what the actual wave would look like. And so if you had two, let's say, water waves or two waves on a string going towards each other, as they are overlapping, they have some like weird funky shape. You can test this for yourself if you get like a jump rope and two people, one on either side of the jump rope, and each of the two people starts like waving the string around as they overlap. Okay, you can actually see the wave on the string as they overlap. It looks like some weird funky shape. Okay, and so that's an example of superposition. So remember, superposition is just the idea that when two waves occupy the same point in space, you add the displacements together. Okay, and then because of superposition, you have two types of interference, either constructive or destructive interference. Okay, and so as we go through the notes, you can pause here and read what it says, but it's basically just talking about what we just talked about before. Constructive interference is a type of interference where the resulting amplitude is greater than the amplitude of the two individual pulses by themselves. Okay, in other words, you add these two waves together and you get a bigger wave. Not to be confused with destructive interference. Remember, deconstructive interference is not a thing. Okay, destructive interference always involves some type of cancellation. So down here you can see two wave pulses going towards each other. When you add 1 plus -1, you get 0, right? The two waves cancel each other out. That's destructive interference. Okay, now one example of where you might see this is, for example, noise canceling headphones. Noise canceling headphones basically have a microphone that takes in the sound around you and emits a sound designed to cause destructive interference inside your headphones. In other words, the headphones listen to the sound around you and emit their own sound to cancel out the outside noise. And so that way, if you have noise canceling headphones on, you can hear the music that you're listening to, but you can't hear conversations going on around you. And this chart kind of shows you the example or the difference between constructive interference on the left and destructive interference on the right. And again, it doesn't have to be perfectly destructive interference. Here you can see they're the same size, and so when you add these two together, they completely cancel out. But destructive interference does not have to involve complete cancellation. Okay, so just to do two really basic examples, example 1 says find the superposition displacement of the two waves shown. Okay, well, we have two wave pulses going towards each other, one with size 2, one with size 4. Superposition says that when they occupy the same space, they're going to add their displacements together. 2 plus 4 is 6. Very, very easy. Now, is this going to be constructive or destructive interference? Well, if they're the same sign, in this case they're both positive, it's going to be constructive interference. Right? Very easy example. Okay, so pause it there if you need to look over that. Okay, now example 2, let's see if you can figure out example 2 on your own. So pause it here, see if you can answer example 2. Okay, so example 2, find the superposition displacement of the two waves shown. The one on the left has a displacement of 2. The one on the right goes down 1, 2, 3 units, so it has a displacement of -3. And so when they superimpose, they add together, they're going to form a new wave of size -1. And now this is going to be destructive interference, right, because they're opposite signs. One is positive and one is negative. Okay, so that is it for example 2. And then just to do one more really quickly, example 3, it says let me adjust the size so you can see this a little bit better. It says two pulses with amplitudes of 5 units and 2 units move toward each other on a stretched string as shown. The pulses have the same speed and are equidistant from point P, which basically means they're going to meet in the middle at point P. Which diagram best shows the resultant pulse when the centers of the two pulses are at point P? Well, again, we're going to get superposition when the two waves overlap. This is basically going to be like +2 coming in from the left, plus -5 because it's going down 5 units, plus -5 coming from the right, and that's going to give us a superposition displacement of -3. So the answer to this question is going to be A. This is definitely an example of destructive interference because they have opposite signs. We have one positive wave pulse and one negative wave pulse. Remember, if they're both positive or they're both negative, it's always going to be constructive interference. If they have opposite signs, it's going to be destructive interference. Remember, Deconstructive interference is not a thing, so please don't use that term. It's constructive, like you're working in construction and you're building something up to be bigger and better, or destructive as in like destroying something, cancellation. Okay, so that's the example, that's the difference between constructive and destructive interference. So in this video we talked about diffraction, and then superposition and interference. And remember, any type of wave, whether it's water wave, sound wave, light waves, all waves can experience all of these types of behaviors. Okay, so you can have interference with sound waves. You can have interference with light waves as well. Okay, and we might talk about that later on. But for now, we're just going to talk about the basics. Okay, so that covers it for wave behaviors. We've talked about reflection, refraction, diffraction, and then superposition and interference. Okay, so please let me know if you have any questions. I'll see you in the next video.